So the specific instructions that we were given on this thing were to use the integration tables. And I will just point out that there might be a way to get through this without using the integration tables. I have a technique to get through it without using the integration tables. Not using a technique that's in our textbook though. So I think with this, it's possible that integration by parts would get us somewhere, but we don't have to worry about that because the instructions on the problem specifically were go straight to those integration tables, right? So I'm going to pull up the integration tables and start looking for something that looks like this. Now there are like the different parts of the integration tables. I'm probably looking for the square root part. If we look through, if I look through those tables, so I am looking at, so the first set of square roots talks about forms involving a plus bu. That's not really matching what we have. So I'm going to keep going and look for something else with square roots. So if we go a little bit further, there's a section on forms involving the square root of u squared plus or minus a squared, which is kind of almost what we have, right? Usually in this form, the u is our variable and the a would be some kind of constant. So we might be able to make one of these forms work, but let's keep scrolling and see if there's a section that matches a little bit better. And if we go down just a little bit further, there's a section that looks like a squared minus u squared. And this is the section that's going to match better with the form that we have. There's probably a way to make it work with this one. This is not going to work because our variable is squared. And so if it were going to be something like this, we would expect a 2x somewhere to be able to do a U-substitution. So now I'm looking at my forms that have this, right? And I'm thinking about a being equal to 1 and u being equal to x. And it looks to me like equation 34 is the one that is going to swoop in and save us. So equation 34 matches what we've got because equation 34 looks like u squared square root of a squared minus u squared du, which if a is 1 and u is x, that's what we have. This formula says that we should have negative 1 over a, natural log of a whole bunch of garbage, a plus the square root of a squared minus u squared, whole thing over u plus a constant. So really, the bulk of the trick to these is just figuring out which of the equations in the table we need to use. Question? So if we look at equation 33, 33 has a u right here instead of a u squared. And since we have an x squared, not just an x, equation 30, oh, did I write the wrong thing? Oh, I wrote the wrong thing. I got off a line. Cool, thank you. I got off a line in terms of the formula. Negative 1 over, okay, thank you. Honestly, I do so much better if I have them printed out. I just need that little bit of visual. Okay, does that look more like our equation for 34? Awesome. So the only thing that we have to do is plug in 1 for A and X everywhere we see a U. So I'd be looking at negative square root of 1 minus x squared over x plus a constant. Now there's a question in the chat that I was ignoring because I wasn't quite sure what it was referring to. There's a question about going through both. I'm not sure if that meant trying to integrate this thing without using a table, if that's what the both was. Sure. Anyone like to see me struggle with this and see if we can do it without a table? I'm willing to talk through what my process would look like. Sure. My recommendation is to maybe not take notes until we figure out if it's going somewhere. This could be me just trying stuff. So we've got 1 over x squared and a square root of 1 minus x squared in here. So one thing that occurs to me is square roots are pretty gross. I'd kind of like to find a U-substitution in this. It'd be pretty nice to have a U-substitution. There are a few ways that I could try to force a U-substitution to show up. One that I was thinking about you might try to multiply the top and bottom by x so that you'd have the x that you need for the U-substitution on the top. The problem is I'm not really sure what we would do with an x cubed. So I'm going to think a little bit outside of the box and just see what happens if I were to let U be equal to this whole thing. Well, if U is equal to this whole thing, then U squared would be equal to 1 minus x squared. And if I'm thinking about U substitutions, I'm trying to build my vocabulary list, which means I know what to do with the square root piece now. And I also kind of know what to do with the x squared. So if I'm trying to figure out what to do with the x squared, I can add x squared to both sides and subtract the U squared. So now I've got something to exchange my x squared about, and I've got something to exchange the square root part about. I just need something in my vocabulary list to deal with the dx. So I know that 2x dx would be equal to negative 2u du. And this is where I would go, yeah, I'm still stuck. I still don't have this x that I need. There isn't really a way, there isn't really a way past this. I'm still stuck. Well, if I divide by 2x, right, sure, I can certainly solve for dx. But if I rearrange this to say dx equals, I would have negative u du over x. But if I borrow an x from over here, then I don't have the x squared anymore. So we're kind of just going to roll around in circles. I'm going to address the question in the chat, and then I'll go back to, I do actually know how to solve this. It's just going to be unconventional. But there's a question in the chat about to actually do the problem as it was stated, right? We're using the integration tables, which comes down to identify sort of what form it is so that you can find that section of the tables. And then within the formula, figure out what your A, B, and U are. This particular one didn't have a B, but a lot of them have an A, B, and a U. Yeah. Okay. So back to this thing. That didn't get me anywhere. But you know what will? A U-substitution with trig. You all can decide if this is worth our time. I will get it set up, but I know that 1 minus x squared, if I reimagined that to say 1 minus sine squared of something, I know that that would be equal to cosine squared of the something, which means I'm going to make the substitution to actually let x be equal to sine of t. By doing that, my dx would become cosine of t dt. And the overall integral would look like 1 over, well, x squared would become sine squared t. Inside of this square root, I'd have 1 minus sine squared t, but that's equivalent to cosine squared t. And the square root of cosine t squared is cosine t, which means I'd end up with 1 over sine squared t cosine t times cosine t dt. And now we're almost there. We just have to remember that 1 over sine is secretly cosecant. And with that, I can say, oh, whose derivative is that? Awesome. I'm going to pretend everybody said negative cotangent plus a constant. And then this is where the really extra fun part would come in. You know how usually we do a U-substitution and then we have to like plug the stuff back in? Well, to plug the stuff back in, I would draw a lovely triangle for myself, because if x is equal to sine of t, then my angle was t. Sine of t would be opposite over hypotenuse. I know this missing side from Pythagorean theorem would look like 1 minus x squared. And now cotangent for this picture, tangent would be opposite over adjacent. So cotangent should be adjacent over opposite. That adjacent side was the square root of 1 minus x squared. And then the whole thing would be over that opposite side plus a constant. Hey, look, that is exactly what the table told us. Woo, we win. You know why we win? Because we didn't have to do that. The problem said use the table. We should definitely use the table. If I didn't convince you that we should use the table, we should use the table. Yeah. So, I mean, just from a practical standpoint, most of the formulas in the table are because you have to do gross things to get there. Should we look at another one from homework 16? Are there any others in homework 16 that somebody wanted to walk through? Yes, I'm with you. Table is better. That was the only one someone had emailed me about ahead of time, but I'm up for whatever. Yeah. So typically what a quiz or exam problem looks like for the table is that you're given part of the table, like as a cover sheet to the test or something. I have never in 16 years seen anyone expect you to memorize anything from the table, right? Like the point of using the table is being able to manipulate the question to fit something in the table. And that can be tricky and they can be hiding a little bit. So yeah, let's take a look at the second one from there. And I'll move this as needed in just a second. But ln of 5x squared dx. Okay. So I'm gonna have to pull up the table. Oh, by the way, this one is more doable without the table. This one's a couple of integration by parts. It's messy, but it's not horrific. We could do this. But again, the problem told us to use the table. So I am going to the portion of the table. I think we only have one part of the table that involves ln. And there are only a few formulas in there, but the formula that I'm looking at is for the integral of ln of u squared du. And that the integral of ln of u quantity squared du is going to turn into u times 2 minus 2 ln of u plus ln u squared plus a constant. So now the only thing that we've got to do is to deal with our u. Now, when I say deal with, that means we're going to end up doing a U-substitution because I need that 5x to be my u so that it's matching up with stuff over there. And once my pen starts writing, which it will, I have faith. I have faith in my pen. Come on, little pen. Okay, so if u is equal to 5x, then du should be 5 dx. And if I go to translate this thing, that means that my dx is 1/5 of du. So I am looking at, if I pull that 1/5 out in front of the integral, now I've got 1/5 the integral of ln of u du. Now, sorry, ln of u squared, it was squared. So now I have exactly this formula, just times 1/5. So 1/5, and I already know that u is 5x, so I can go ahead and plug that in when I'm writing it. So I've got 1/5 times 5x times 2 minus 2 ln 5x plus ln 5x whole thing squared plus a constant. Sure. Yeah, you can definitely cancel the 1/5 and the 5. There is a request in the chat to look at the last one on there, the definite integral that's on there on homework 16. I'm happy to do that one too. Happy to do other things as well. I can also make some things up to practice more with the tables if that's what we are most concerned about in this moment. But that is the last one on there. So I would be thinking about like scanning through the tables and throwing pens. I would be thinking about throwing pens. But the part that stands out to me as kind of the messy piece is this thing on the bottom raised to the 4th power. Generically, that thing on the bottom looks like an a plus bx to the 4th power to me, or like an a plus b u to the n. So that's sort of what I'm looking for as I'm scanning through the tables. So now I'm going to go scan through the tables. And I think I'm looking at 5. So formula 5 that we would have to try to make this, that's the one I'm thinking we're going to try to make it fit. And so I do understand why there might have been a question about this one. So if I look at formula 5, that looks like the integral of u over a plus bu to the n du. So just kind of comparing it to what we have, I'm thinking about a being equal to 1, b equal to 3, u equal to x, and n equal to 4. I don't know whether it's worth to, like, is it helpful to watch me plug all the numbers in? I really have no idea. Would anyone like to watch me plug all the numbers in? I got no takers in the room and no takers on Zoom at the moment. So let's not plug all the numbers in. You can look up the equation and plug all the numbers in. I find this a really boring section of the book. Sorry. Trying to get excited, but I can't. Anyone want to see me do this a completely different way? This one's actually not terrible as a U-substitution. I know it looks like it would be, but as a U-substitution, I'll pull up the original problem again. Let me just rewrite it. 0 to 3 x over 1 plus 3x to the 4th dx. I mean, it's going to get a little messy, but as a U-substitution, hope I'm not getting myself in over my head. I'm pretty sure it's going to work. I'm going to let u be that messiness on the bottom, the 1 plus 3x. Well, in the spirit of my U-substitution is all about creating a vocabulary list, du is going to be 3 dx, which means 1/3 du is equal to dx. So I've got something to translate the dx to. I've got something to translate the bottom to. The piece I don't have something for is the x on top. But this is where I'm going to get creative and take that top equation, but rearrange it to say x equals. If I plug all of that stuff back in, this maybe I want to think about as like 1/3 times u minus 1 is x. I've got that x on top, so I'm actually going to pull the 1/3 out in front. So that 1/3 is coming from replacing my numerator with u minus 1. I need another 1/3 that's going to come from dealing with my dx and turning dx into 1/3 of du. And then the bottom is u to the 4th. This is so much better than the thing that we started with. And if we had just started here, we'd be in really good shape. Because the only thing I would need to do is to break that apart into 2 fractions. So I've got that u over u to the 4th, which I'll turn into 1 over u cubed minus 1 over u to the 4th du. And I think better in negative exponents, so I'm going to write that as u to the -3rd minus u to the -4th before I integrate it. Now when I integrate it, I'm going to have u to the -2 over -2 minus u to the -3 over -3 plus a constant. And then we can plug back in what we got to begin with. So I've got 1/9. U was 1, we'll call it was 1 plus 3x to the -2 over -2. Minus a minus, I'll go ahead and make that plus 1 plus 3x to the -3 over 3 plus a constant. And if you did plug all the numbers in, that should look a heck of a lot like the formula. I think the formula puts these in the denominator instead of giving them negative exponents. But other than that, we should have gotten the same answer as using the formula. Oh, but we're not done. Thank you. Thank you, Zoom. This was a definite integral. So we now don't have a plus c. We actually have to go back in and plug in the 0 and the 3. That's going to be messy, but you all can handle it. Just make sure that when you plug in 0, it's not like things don't all magically go away. Like they do sometimes with zeros, but they're not for this particular one. Okay, folks, we got 20 minutes left today. What else are we working on? You can, you could do this with integration by parts. You should be able to do this with integration by parts because that x in the numerator, if you take the derivative, it'll be 1. And the other piece of it, you can certainly integrate or differentiate. So you should be able to get through it with integration by parts as well. Would anyone like to see me do it as integration by parts? I've already passed calculus, so you know, I'm here for you all. Dun dun dun. So we're into the really boring part. We're genuinely into the really boring part. So boring that we should not have class on Friday. We're not going to have class on Friday. So midpoint rule, trapezoid rule, and Simpson's rule are just two other sets of formulas. And unlike midpoint rule, you get to just, like, the points that you're going to plug in are even easy to find. So really, we're into this section of the book where we've got some formulas. Do you want to see some interesting calculus instead of formulas? Just for fun today? I'm getting us like ahead of the formulas. We're not going to meet on Friday. I don't need, like, if you're struggling with the formulas, totally, absolutely go to drop-in tutoring, but you're not going to struggle for long. They're not that bad. But preview of coming attractions. Okay. I'm going to give us an area problem just for practice. So you all are going to find this area on your paper. You got this, don't worry. Here's my function. I'm going to keep it pretty easy. This is y equals 1 over x. And let's integrate from 1 to 4. Don't use trapezoid rule. Don't use it, like, just actually do it. So set up the definite integral and evaluate that definite integral. You got this. Practice finding the area. I'm really curious. I managed to make using the tables interesting. No, I know. See, I'm sure he is bored out of his mind too. Like, I'm not even sure why it's on the department syllabus.
I'll ask him later if it's gonna be open.
Yeah. No, I'm positive that you want him to memorize them. He's going to give you. Yeah. Yeah, he'll either give you the whole table or part of the table, but you do not have to memorize them. It would be a waste of your time. Don't do it.
Has he set up the final movie?
It is.
No, but I'm really confused because on his syllabus, it says that the final is also just 30 minutes. Yeah. Even though we should have 2 hours and it's on finals week, but it's only 30 minutes. So how is he gonna do a cumulative exam in 30 minutes? Yeah, he does say that.
I wonder if that's a typo on the syllabus. Someone should ask.
Because he said it was 4 tests, each weighted 25% of our rate, each 30 minutes long.
Okay. Oh yeah.
Yeah, I'm like, I just don't see how he's gonna, like, I don't know. I feel like we'll just have one question from each.
So here is a way that I could write one question that encompasses 12 things, right? I could ask you to find the area of something that required you to do integration by parts, right? I could ask you to do something that we're in the probability section, which is kind of the last thing that we cover in 16B. There's lots of opportunity there for me to be creative about giving you integration stuff. So he might not, it's cumulative in the sense that it wouldn't explicitly be testing you on integration by parts or U-Substitution or something, but the question might require you to do it. And so that could be how he's going to make it cumulative in that sense. Yeah. Oh, are you already done with this integral? Probably, because it was quick. Yeah. Okay.
But not too easy, just like, I feel like I might have done on.
No, you probably didn't. I really was trying to make it very straightforward. Okay, so my area, I'm looking at 1 over x dx from 1 to 4. Cool, because that was my function. And if we integrate that, what do we get? totally. And I'm doing that ln of x from 1 to 4, which means I'm gonna get ln of 4 minus ln of 1. But then we're gonna do the thing that he always does on solutions. We're not even gonna write the ln of 1 because natural log of 1 is 0. Okay. That wasn't really the question I wanted to ask. You ready? Same graph. But what I really wanted to know is the area from 1 to 4,000. Don't think too hard, because not very much changes in that integral. I got the, oh yeah, sorry. It is the same function, 1 over x. Should have told you that. It's still 1 over x, but instead of going to 4, I'm going to 4,000. So we're going to do the integration and we're going to get natural log of 4,000. Okay, wait. That wasn't really the area I wanted to find. I wanted to find the area if I keep going forever. Dun, dun, dun. Don't think too hard. What's the area going to be if I go forever? Yeah, and natural log of infinity is going to be infinite. Backwards. Natural log of 0 gives you negative infinity, but natural log of infinity is going to infinity. I understand where your 0 is coming from because I've drawn this graph. This graph is headed to 0, but the area under the curve is heading to ln of something. Okay, so we got to get a little bit of notation down for a second. That idea of taking this forever, we're going to bring back something from 16a, our favorite 3 letters, L, I, and N. Yes. So I'm going to think about this as the limit. And because I'm already like using x in the integral, I need a different letter to use. The book chooses B. I'm just going to go for it. B for a really big number. I don't know. We're going to let B go to infinity, but our setup is going to be the same. We're integrating from 1 to B. We've got this 1 over x dx. We know the answer is going to be infinity, but notation wise, mathematically, we're going to bring that limit along with us. We're going to evaluate the integral. We're going to have that natural log of x from 1 to b. Still bringing that limit with us because we haven't actually evaluated it yet. And then we're going to say, okay, the natural log of infinity goes to infinity. ln of 1 is still 0. Yeah, it is divergent. To throw some more vocabulary in the mix. It is indeed divergent. Now, a logical person, especially a logical person who has not seen strange things happen mathematically in calculus, would probably think, yeah, duh, no matter what I integrate, if I add that area up forever, it's going to equal infinity. So I'm going to change our function just slightly to be y equals 1 over x squared. And I'm also going to want to integrate this from 1 all the way to infinity. So in terms of setup and like practicing our notation here, we're kind of going to create a wall for ourselves out there at B, and then we're going to push that wall to infinity. So I'm going to have a limit as B approaches infinity. set up our integral, 1 over x squared. And we're gonna integrate from 1 to b. Because we're just like pushing that wall out. What do we get when we integrate 1 over x squared? Or if you like it better, we can think about that as x to the negative 2. Be brave. Oh, yeah, but like specifically, if I integrate x to the negative 2, what's my antiderivative going to look like? I'll take it. And now we're going from 1 to b. Think I got space to squeeze this in? So I'm taking the limit as b approaches infinity. That x to the negative 1, if it's okay with you, I'm going to put it in the denominator. So that this actually looks like negative 1 over b minus negative 1 over 1. Now this part relies on you having some 16A memory, which depending on when you took it, maybe you do, maybe you don't. But I've got 1 divided by infinity here. If I had $1 and I decided to be generous and share it with everybody at UC Davis, how much money does everybody get? Barely anything. Like how barely anything? Like 0. You get no money. 1 over infinity is headed to 0. So that means that what I actually get here is 0 plus 1. This is definitely convergent. And you don't have to think that that's mathematically interesting, but I promise you that Professor Ma does. Yeah. Yeah.
Can you rewrite the x to the negative 1 over negative 1? How you rewrote it below?
Oh, yeah. Yeah, for sure. So I can squeeze this. I can squeeze this in. So I've got a limit as b approaches infinity, and this is negative 1 over x from 1 to b. Is that what you mean?
Yes.
Yeah.
Okay, that makes sense. And then also, can you define like divergent versus convergent?
Totally. So if I get infinity, we say that it was divergent. If I get any number that's not infinity, we say that it's convergent. There will be more to both of those words in 16C for any of you that are sticking around for 16C. Yeah. So you don't have to think that's interesting, but mathematicians think it's really interesting that we took this thing. If this were a wall, that wall goes on forever. It never ends. But I could paint it. I could paint it with 1 gallon of paint. Okay, that's really a bad analogy because those units don't really work out right. A gallon is not a measure of area, but you know what I mean. This has an area of 1, even though that wall is infinitely long. Moderately interesting, maybe. We're gonna have more fun with that after we fight through the boring stuff of trapezoid rule and Simpson's rule. So I will plan to see you all again on Monday, not Friday. Also, don't forget, tomorrow's a university holiday. So there is no tutoring tomorrow. You should not have any of your classes tomorrow. There is, however, tutoring today until 4 o'clock over in Sheila's library, lower level. And there will be tutoring Friday and Sunday, and it's just Thursday that there's a pause in tutoring because of the holiday. I will stick around for a couple minutes in case anybody had a last question, but I just don't know what else to cover today. So I think I'm calling it.
You know if they're gonna add a whole 16C class?
So I'm gonna go with no, and part of my no is that when I asked, you might be the only one in here taking 16C because a lot of majors don't require it. And so there's just a huge drop off in the number of students that need 16C. So I don't think there's gonna be a co-class for it. But for sure, we will still have office hours. There will still be tutoring. You're totally welcome to come to any of that stuff. Yeah, but there just aren't a ton of students. Now, if you have 15 friends that all have a similar gap in your schedule and you come to me and say, hey, can we have a co-class for 16C at this time? I'm bringing 15 of my friends. I got you. Okay?
I'm gonna make 15 friends.
You better go make 15 friends. Yeah. Yeah. The last time we tried offering a 16C co-class in winter, literally 2 people came. And so it's more productive at that point to just have office hours. Yeah. Okay. The weather has cleared up. It looks like a nice day out there. Time to head outside. Time for me to go kayaking. Yeah,